All right, let's go ahead and get started. This is CS4510, L02A, and this is on DFAs, which are deterministic, finite automatons. So a DFA is like the first model of computation we do. We study DFAs for two reasons. One, they are so simple that they actually become mathematically interesting. They're very toy-like. And the second thing, we need to study something. We need to start somewhere. So we're going to start with studying the DFA. And then from there, we can like make extensions of it, and we can study other things. But it's just a baby's first DFA. So what is the motivation behind a DFA is really the simplest model of computation you can think of. Consider the way your brain works cognitively. Ideas go in and out of the back of your mind. Some things are stored and then they're recalled and then they're kind of there, right? And certain things appear to have, they're just stupider than us, you know? So they're like, let's simplify everything and make it as simple as possible. And the example I always use is my pet rabbit. Down. Okay. It has 2 brain cells, max. Okay. It eats and it sleeps. That's it. It has never showed any other emotion besides those 2 states of mind. And in a literal sense, as in state of mind, right? These 2 brain cells operate and they take the forefront of the mind in a different order of a function of the sensory inputs that the rabbit receives, right? There are like, it touches grass and it experiences things, and all these things operate as some function to say which is the current state of mind, right? Which one is the one that's being stored and which one is the one that's recalled forward in the operating condition, right? And we can say that the operation between these 2 states is a function of one thing specifically, is whether or not there is food in front of the rabbit, right? So if the rabbit is asleep and I place a carrot in front of the rabbit, she'll smell it and wake up and begin eating it, right? So if I place a carrot in front of the rabbit, that's a sensory input to the rabbit to translate the rabbit's brain into the other state. So it switches states of mind. And the way we represent that is with what's called a transition, which is really just an arrow. And then we can put a little carrot here, right? So you can go from the sleeping state of mind to the eating state of mind upon smelling or eating a carrot, okay? Now, let's say you're in the eating state of mind and there is still a carrot in front of you. What should happen?
You stay in the eating state of mind?
You stay in the eating state of mind. The way we represent that is with a loop like this. Okay. Now, let's say you're in the eating state of mind and there is no more carrots. You should transition to going back to sleep. There's no more food. So what you do, we represent it like this. There is no food, right? And let's say you're sleeping and there is no food. What should you do?
Stay in the sleeping state.
Yeah. This is all a DFA is. It's just, you have some finite states and then you transition between those states as a function of things that are seen, right? And in fact, if you were to consider a sequence of inputs, for example, carrot, carrot, no carrot, no carrot, carrot, you could determine what the current state of mind is. That's really all a DFA is. So we'll spend the first part of this giving a definition, and then we'll just do a couple examples of DFAs. And you should think of a DFA as like a programming language, right? There are a couple parts to a DFA. We have, it's a tuple, Q, sigma, Q0, delta, and F. And these 5 parts operate in the following way. First off, there's a finite set of states of mind. It's important that the states of mind be finite. We'll talk about this in like a month. But I asked you earlier, like, sigma is also a finite alphabet. Maybe we call it AB. It's a finite alphabet. I asked you, why is it okay if the alphabet is finite? Why is it okay if the number of states of mind is finite? And again, for Q0 to Qk, consider like this rabbit has two states, eat and sleep, right? This is, again, a conceptual, open-ended question, not with a right answer right now, but.
Does he have like a holistic view of all the possible transitions that could occur?
Sure, but could an infinite number of states of mind give you anything?
You asked for finite or infinite?
If you have finite states, I claim that's the definition. But suppose I asked for infinite number of states. Would anything change? Yes.
I guess you could argue that it could be theoretically infinite, but like some of the states might not actually be used. I guess
It's also really good intuition.
it's similar logic to, I guess, the language thing. So it's like, realistically, I guess for most scenarios, you'd probably only want to use a finite amount since it's something to represent.
Yeah.
And also, if you have a finite language, it makes sense to have a finite number of states, like a finite number of outputs.
But the only thing I would say is that some of the languages we want to consider won't be finite, but they'll be made of finitely many symbols. The languages themselves could be infinite, as there are, for example, infinitely many prime numbers. But exactly what you said, it's like some of the states may not be used in some sense. So like in a realistic scenario, if we're trying to model computation, that is the first answer. The second answer is that it's on your homework. I'll make sure it goes out on homework 1. To prove that if you have infinitely many states, it's actually too powerful. It's kind of boring. It's not a good thing. But really the whole class is studying finite structures and like what can this finite thing do to describe an infinite set of strings. That's what we'll talk about soon. Let's just finish the definition. Q0 is a designated start state. It's just the entrance, the first line of code. You got to begin somewhere. We just call that Q0. Delta is a finite function which takes takes a single state and a single symbol and outputs a single state. And it's well defined. Now again, these are finite sets, so this is a finite function. This is really a table. And the way we write this is like, if we say delta of qi comma a is equal to qj. What we really mean is you're at some qi. If you read an a on the input, you'll go to qj. Right? Now, this is, the transition function is how you define the movement between the states. But how do you accept? So what we do is we say these are our final or accepting states. Is that if the computation terminates on one of those states, we just say the machine accepts. If the computation does not terminate on one of those states, we say the machine rejects. So this is the formal definition of a DFA. Now, formal definitions are always more cumbersome to work with than just a bunch of examples. So if there are no questions on the formal definition, we can just get started and do a couple of examples, right? Are there any questions on the definition? Right. So let's do, W is in sigma star, such that W begins with an A. Right. So we're going to make a DFA for this language, right? So what we're going to do is we're going to start somewhere. So we'll say we start at Q0. And oftentimes we draw an arrow from nothing, or a little start label on the arrow from Q0. And in fact, if you typeset this with LaTeX, it's defaulted that the start state has a little arrow with a little label of start. And if we begin with an A, the way the DFA computes is it takes the transitions as if it was reading the string left to right. It cannot go backwards through the string. It cannot jump to the end of the string or the middle of the string. It cannot do anything, but it goes through the string left to right only. So if we're at Q0, what we can do here is we can make two states. We can call this Q1 and we can call this Q2, right? And if we see an A, let's go to one of them. And if we see a B, let's go to the other. this is the start of a DFA, but it's imperfect. There are a few problems with it. What are some of the problems with this? Yeah.
It can only consume one token.
Yeah, exactly. So like what happens if you run the DFA on AB? You'll go A, B, it's like, well, what happens, you know? So the DFA transition function must be well defined. What that means is that every state must have 2 outgoing transitions if sigma is size 2. So this, if you're here and you see an A or a B next, you know where you're going, but not here. So what we do here is we want to make sure that, well, we've seen an A, we've seen a B, we want to exhaust the rest of the input. So what we'll do is do this. Okay, now, and this is technically 2 transitions, but we just represent it this way, right? Now, every state has 2 outgoing transitions, so no matter what string you give this machine, it will correctly go to some state, right? Let's say B, A, A, B, you go B, A, B, right? And you should think of it as, again, there's exactly one state of mind. There is a cursor, there is something there that keeps you locally on one state at a time only. That's the determinism part. You're in exactly one state. We'll talk about non-determinism later, but for now you're in exactly one state, right? There's another problem with this DFA.
No end state.
Kind of. I mean, like, I guess the closer thing I would say is that there is no accepting states.
Yeah, that's what I mean.
Yeah, I see. We don't know, like, certainly we know how to move between states, but we don't know which one should be accepted or which one should be rejected. So the first thing is, certainly this state should be accepting, and the way we denote that is like this. We do a double circle to denote that's the good state. So things that land on a double circle state are accepted. Things that land on a non-double circled state, a single circled state, are rejecting. So, second question, is the empty string in this language?
Yes, that would just be the start, I think.
The empty string does not begin with an A, though.
That would just be at the start point, Q0?
Yes, on every DFA, the computation of the empty string just lands there. It's like begin and end there, done. But the empty string should not be accepted. So we would not make Q0 an accepting state. We would not double circle Q0, is what I'm saying. Right. Now this is the DFA. There's 2 ways to do the DFA. First off, just the picture. If I ask for a DFA, just give me this diagram. That's easy, right? And in some sense, this is our first automata. This is a very limited programming language, right? It's very simple, and you've seen this in some other class, right? What class was that?
2110.
Yeah, you saw state machines in 2110. When I took 2110, I did not remember seeing state machines, so either it was not taught to me or I wasn't paying attention, but you should have seen this in 2110, right? The term state in computer science comes from the term state of mind. This is like the origin. And basically all DFAs are state machines. It's all it is, right? There's a little more syntax around it, but that's basically it, right? 2 things we can say about this is the diagram is one way to define a DFA. Another way is using the 5 parts, right? So we could give the 5 parts. What are they? Q, sigma, Q0, delta, and F. Let's just do it. Q0. Q is going to be 0, Q0, Q1, Q2. Sigma is going to be A comma B. Delta is going to look like the following. Right. So if you're at Q0, Q0, Q1, Q1, Q2, Q2. If you're at Q0 and the possible combinations are A, B, A, B, A, B. If you're at Q0 and you see an A, what state do you go to? Q1. Put a Q1 here. If you're at Q0 and you see a B, what state do you go to? You go to Q2. You're at Q1, and you see an A, you stay in Q1, and same if you see a B. Similar, if you're at Q2 and you see an A or B, you stay in Q2. So the transition function could be written as this table, but this is kind of like difficult to read, so nobody does it this way. But know that it's the formal definition. The transition function is just a lookup table. It's just like, it's a finite function from a finite set to a finite set, and the output is also a finite set. So this is really the transition function. But this is kind of annoying. So we really look at the, we'd rather prefer a diagram like this, right? And then finally, what are our accepting states? F is just only Q1 and nothing else. Right? So this would be the 5 parts, and of course Q0 is just Q0, but these would be the 5 parts of our DFA, right? If we were to do the formal definition. But notice that the picture basically contains all this information for us. It tells us which state is starting, it tells us what the states are, what the alphabet is, it tells us what states are accepting, it tells us all the transitions. So the diagram is just as good and indefinitely preferred, right? Let's give more commentary on this program. Like, what can you do with the DFA or can't you do? So like you could make an analogy here with like a high-level programming language as one that takes constant memory, right? This machine does not have access to variables. It can't write anything down. All it knows is where it is at that moment. And so there's an analogy you could make to, like, every state has some kind of meaning, right? For example, let's say you have some structure that looks like this. If you're in this state, you know that you just saw an A, right? Then if you're in this state, you know you just saw an A, coming from the state in which that you just saw an A. So you actually, when you are in this state, you can assign a meaning to the state, which means that I know I just saw 2 A's. That's kind of analogous to if A of, let's say I is equal, let's say W of I is equal to A, and then if W of I plus 1 is equal to A, hashtag to do, right? When you're in a programming language, when you're writing code, when you're in a specific line of code, you also know certain conditions have been met. And the best way to think about a DFA is not in some sort of memory structure, but that each line of code, each state is actually analogous to a line of code. And the flow between the states is analogous to what is the current, the pointer of which line of code are you currently executing, right? Something like this. And if you're at this nested if statement 2 levels down, you know certain conditions have been met for you to even reach there at all. Same thing when you're here, right? So these things are analogous in some sense. And there are all kinds of little programming tricks you'll see as we get comfortable drawing DFAs. For example, when we do a self loop like this, that basically means ignore it. So if we see a self loop like this, that means like just whatever comes after, just throw it away. So this is in some sense trash. The other thing is like one of these states is accepting, one of these states is rejecting. And these in some sense are like 2 purgatories. The structure means that you can never escape. You enter one, you enter the other, you'll never get out. So the only thing that really matters for this machine is what the first symbol was. Nothing else after that matters. Are there any questions conceptually about DFAs or anything like this?
What is the meaning of F again?
F in the DFA is finite. Yes. So on the homework, you'll have something called a DIA, and you'll be asked about it. But F is finite, and that turns out to be very important. Deterministic is also kind of a charged word, and we'll talk about non-deterministic NFAs next time. So there will be a difference there. The automata is just there to call it something, right? But the F is for finite, yes. Oh, you mean this F?
Yes.
I'm sorry. This F is the accepting states. So the ones with the double circles, the ones that accept.
Oh, gotcha.
Yes. More questions on the DFA? Conceptual programming questions? Okay, I'm going to give you a couple. Here's another question. Okay, so fine, it takes constant memory. How much time does DFA take? O of 1 on an input. Let's say this DFA has 3 states. Let's say you gave it a word of length 1,000,000.
O of n, however long the string is.
You can even give a more precise answer than using big O. Pretend we don't have big O.
However long it takes
Almost.
to transition between each state.
The answer I'm looking for, it's not just O of n, but the time, quote unquote, is literally n. Not just O of n, but it takes n steps, where n is the length of the word. Right? It literally takes the length of the word steps. Why? Let's run this DFA on BAABA, right? B, A, B, A. Reject. That took 5 steps. Right? So computation on a DFA not only takes linear time, it takes quote unquote real time. It's exactly the length of the input to decide such a string. Right? Another, again, a huge limitation. It can't go backwards. It can't jump to the middle. It can't store things in variables. So it appears to take linear-ish time. How much space does this thing use? Like, you've never been asked to measure space complexity, and the definition of such a thing is also quite difficult. But if you had to conjecture, how much space do you think that is going on here?
There's space required to store the states and transitions.
Sure. Or the space used, the memory, as it grows as a function of the input when you execute a DFA on a word.
It shouldn't grow because you don't store anything that store anything that happened before. Like each transition state doesn't add any memory to store.
Exactly. It's basically constant. It takes no memory in some sense. It's rather than zero memory, we could say constant memory. Right? Okay, let's do another DFA. Suppose I did W was in sigma star. Says that the number of A's in W is even. If you had to hypothesize, how would such a DFA be written? Give me a starting diagram.
I guess 3 states total, Q0, and then
Okay, let's start with Q0. Always start with Q0.
okay, Q0 that would be a ending phase, like you accept if
Okay.
you are on Q0, since that's the empty word. If it's empty word, you have 0 A's. So
Correct. Empty string is definitely accepted. So it is 0A, so we're going to start there. Now what happens if you see 1A? Should you still accept?
No, you should not. So you go to new state. We'll call it
Oh, Q1.
Q1, I guess. For there's an odd number of A's.
Okay. Now let's say you're at Q1 and you see an A. What should you do?
You want to move to a new state where, since you have an even number of A's, so we can call that Q2.
Okay. But I'll tell you that we can actually do it simpler than going from Q.
Oh, you can go back to Q0.
Yes. In this specific case, sometimes you need more states, but for this specific one, I know you only need 2. Okay. Now what happens if you're at Q0 and you see a B? What should you do?
You stay.
Yeah. And what happens if you're at Q1 and you see a B?
You also stay.
Okay. Is Q1 accepting?
No.
Okay. That's the DFA, right? It basically is a clock. I mean, that's all it is. A. B, 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 B. B's are ignored, right? It just keeps track of the parity of the number of A's seen. And notice that's okay to do with finite memory. You don't need to count the number of A's and then see if it's divisible by 2. You just need to like pair up all the A's and just go between these two things one at a time until you make sure that you know that if you are in this state, you just saw an odd number of A's because you're coming from the state that was for an even number of A's. And if you're in this state, you know you have an even number of A's either because you started here or you're coming from the state that has an odd number of A's. So the only way to end up in this state is to see an even number of A's, and the only way to end up in this state is to see an odd number of A's, and so on, right? So that's kind of the correctness argument. The second comment we can make is the DFA not only moves left to right, it not only is not allowed to jump, it's not allowed to write anything down, it's not allowed to store any information, it also is not allowed to do any pre or post processing. It's not like when it's about to accept, it's allowed to clean up or do anything else. It ends where it ends. On the state that it terminates at, it's done. It halts right there. And like death, it must be prepared for that at any moment. So when you write a DFA, when you do programming on DFAs, you have to take this into account. It's like, that's where I stop, end of story. So I have to be ready to stop at any moment. So even as I'm computing on a word, I must also correctly be able to compute on any prefix of that word. So for example, let's say I do A, B, A, right? I must be able to correctly, I don't know how long this word is. The DFA does not know how long this word is, and I don't know what's coming next. But I do know that I need to be prepared for whatever comes next. So I would go I would go A, B, A, right? But notice that also correctly computes on AAB, A, and the empty string and so on, right? So, more questions on this one? All right, let's do another. What about W is in sigma star, such that the let's suppose I don't want any B's. A to the N, such that N is even. So this is the same language, but there should be no B's in it, right? How could I program such a DFA? We have to start somewhere, so let's just start with Q0. Okay. Now if I see an A, what should I do?
Continue state.
If I see a B, what should I do? Stay at Q0?
Shouldn't be a B, because the language is all A's.
Yes. Suppose the alphabet, though, is
Okay.
AB. You don't want to stay at B, turns out, because you could, for example, do BA, and that may accept or something. If we see a B, we just want to throw away the answer, right? Immediately reject. Just immediately return false. Don't even read the rest of it. What we're going to do is do a purgatory. We see a B, trash. Okay. If we are at Q0 and we see an A, we go here. We see a B, we go here. If we're at Q1, we see a B, we go here. What happens if we're at Q1 and we see an A?
Back to Q0.
Yeah. AB, AB, AB. Which state is accepting?
Q0.
Nope, Q1. Nope, 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 you're right. All right. Yes, okay. Notice the difference between these two, right? Here, B is ignored. Here, B immediate reject. Needs an extra state, though. This ignores B and accepts A, B, well, it'll accept something like that, but this will reject something like that. Even if it has an even number of A's, doesn't matter, it's in the trash can. We don't care to keep track of anything else after that, right? Question on this example? Right, again, we're just doing lots of little programming things so we can see how that works. Okay, let's do one more example. What about W is in sigma star, such that the number of A's in W is congruent to 3 or 4, let's say mod 7. We can do a little bit of modular arithmetic with such a DFA. What should our first thing, what should we do first?
Q0.
Yeah, always. Open a new text file. Start, hit enter, line of code. Done. How many states should we need?
7.
Yeah.
1 for each mod. 7.
The next question you should have, if you have CS brain syndrome, is can you do it with fewer? Certainly 7 will work here, as we're about to see. You can't do it with fewer? You don't think, why not?
7 is prime.
There you go. Formalizing that is actually a little tricky, but that's the best intuition you could ever ask for. Now, what should our transitions between the states be?
you see an A, you move forward. If you see a B, you stay.
Stay where?
Stay at the same node.
Just for all of them, yeah. Okay, what's our accepting states?
Q0.
The empty string does not have 3 or 4 A's. No.
Q3 and Q4.
Yeah. The QI is like, I've seen I's, A's at that point, right? So if I've seen 7 A's, I go 1, 2, 3, 4, 5, 6, 0, right? Nobody ever says 13 o'clock, they say 1 o'clock, right? So mod arithmetic, you go back to the thing. So each state, again, has a semantic meaning. It just means I've seen that many A's. That's all this really means. I've seen 4 A's, 5 A's, and so on, right? We have come up with such simple automatons, and you could generalize this for any n states are required, right? And then you could do any kind of less than n, choose the right states, right? The question is like, okay, we can see that these are all the simple things. So DFAs can do these simple things. Can they do the hard things? So a hard thing would be like, again, W's and sigma star. And then if you cast that to a binary number, is prime. Could you imagine that there's a DFA for such a language? The answer is conceptually probably no. It's like, could you construct a finite set of states that for any number you were to read in binary, you could move between the bits that would accept a prime number? The primes are too mysterious for them to have such a simple definition. So the answer is probably no. But that's not good intuition, and we'll formalize intuition later. But there is, in fact, an even simpler language that also cannot be done by a DFA. Given the limitations of a DFA, can you think of a set of strings that you probably think there is no DFA for?
Empty set.
The empty set does have a DFA. In fact, sigma star also has a DFA. What's the DFA for sigma star?
You accept that?
Yeah. In some sense, these are easy to describe. That's why they have DFAs for them. They're simple. The way to describe this to someone would just be accept nothing. The way to describe this to someone would be accept everything. So in some sense, a DFA is a description of a language. So these two happen to be at opposite ends, but they're so opposite that they're actually easy to describe in some sense. This is a harder thing to describe, but it can still be described by this DFA. Can you think of something that would not be describable by a DFA, that there is no DFA? Can you think of a set of strings that has no DFA to decide it? Conceptually, again, a difficult question. I'll give you the canonical answer. A to the n, b to the n is a natural. Right. Why does this string probably not exist for a DFA? The problem is you need the exact number of A's as there are a number of B's. You need exactly the same number of A's. And how would you possibly keep track of that without some kind of memory structure? We'll prove this later, but this is for any n. For example, you somehow need to reject a to the n, b to the n minus 1, but you need to accept a to the n, b to the n, and then also reject a to the n, b to the n plus 1, right? So to make sure that you are that correct, you need to somehow remember exactly what n was. And it doesn't appear for any n that a finite DFA can do this. So conceptually, it's especially reading left to right, DFA can't do it. In fact, if you were to ask to write a program for this, there's a couple naive things you could do. A naive thing to do would loop left to right, say counter plus plus, COB, counter minus minus. That's one idea. Another idea is just jump to the middle, count A's, count B's, see if those numbers are equal. A couple other things you can do. But all those involve a little bit of memory. You gotta write a couple things down. Here, and the DFA can't write anything down. We'll prove this much later on, but it's like, this is an example of something that's like conceptually DFA can't do, right? Questions on this example? Okay, I'll do one more thing. So you can actually take automaton and then combine them and conjoin them. When you talk about doing code, it's not exactly obvious how you could take code and then combine code. But the cool thing about automatons is the way they're defined mathematically is you basically can do this. So let's say we have two DFAs. We have a DFA, a D1, which would be Q1 sigma, let's just say they have the same alphabet, Q01, delta 1, and then F1. And let's say this decides a language L1, right? And let's say we have a second DFA, D2, Q1, this is a Q2, excuse me, sigma, Q02, delta 2, and then F2, and this decides a language, let's call it L2. And let's make a new DFA D, which is just Q, sigma, Q0, delta, and F. And we are gonna program this DFA to decide L1 intersect L2. So suppose we have two DFAs, D1 and D2. We will construct and make a new DFA D that decides the intersection of the languages decided by L1 and L2. What's gonna happen here is that this new DFA D is going to quote unquote simulate D1 and D2 in parallel, simultaneously on its input. It's gonna pretend it's D1 and D2 at the same time. Now notice it's a DFA, so what it can't do is run D1, rewind, run D2, and see if both accept it. Can't do that, it's a DFA. So it's gonna have to do the simulation in parallel. Here's the definition of D. Of course, we'll give the formal definition and then we'll do like an intuitive example. Q is going to be, well, it could be, if it's simulating D1 and D2 at the same time, it's going to be any possible pair of states that could be in D1 or D2 at the same time. So what we do is we do a Cartesian product of Q1, Q2. So we make a new state in our DFA for every possible pair of states. Sigma is just sigma. That's nice and convenient. If it wasn't sigma, we could still do it, but it's gonna look uglier, so let's just pretend it's nice. Q0 is going to be the start corresponding to as if it started in both DFAs in the same start. It's gonna be Q01 and Q02. Delta is gonna be interesting. Delta, so we want to move between the states of this DFA, but the states of this DFA are pairs of states of the other DFA. But we want to move between the pairs of states as if we were moving between the states themselves. So what's going to happen is going to be delta of, let's say, Qi, Qj. That's the single state of delta, but these are simply the pairs of states here and here. And let's say we see symbol A. We're going to move from this state as if we were moving in both DFAs at the same time, which is going to be delta 1 of Qi, comma A, and delta 2 of Qj, comma A. And again, this is a Cartesian product of states, but it's really one state with two coordinates. And the final state, we want to accept if both accept. So we define the final states to be just the Cartesian product of the final states. Now this is the formal definition of the Cartesian product DFA. Take two DFAs, combine them, you get one bigger DFA. But that bigger DFA does both DFAs at the same time. The formal definition is one thing, but of course what's more useful is always to do examples. So let's do some examples real quick. So suppose I have this language, W is in sigma star, such that W ends with a B, okay? How would I draw such a DFA? How many states do I need? Okay, let's call them Q0 and Q1. What's the transitions between those two states? Hmm? From where to where?
From Q0 to Q1.
Okay. Now, if I'm at Q0 and I see an A, what should I do?
Well, excuse me, if it ends with A rejected.
Yes, but how do we know when we end? We don't know if we're ready to end yet. So I guess the first question is, which state should be accepting, if any?
Q0.
Well, Q1.
Q1.
Yeah. You see a B, you go to Q1, okay? Let's say you're at Q1 and you see an A. Where should you go?
Actually, Q0.
Yeah. You're not ready to end yet. Let's say you're at Q0 and you see a B. We already did that. If you're at Q0 and you see an A, what should happen?
You stay at Q0, you want to continue rejection.
Yeah. You're not ready to end. Now, if you see a B, you go to Q1. Now, what happens if you're at Q1 and you see a B?
Stay Q1.
Yeah. Again, the DFA must be ready to end at any moment. It doesn't know when the end of the string is coming. So it moves between those two states based on the last thing it's seen. If it sees a B, go over there. And if you keep seeing B, stay over there. If you see an A at any moment, go over here, because you don't know if the end is coming yet. So you wait here until you see another B, and then you go back there, right? Now what about, W is in sigma star, says that the number of B's of W is even. How many states should I have for this one?
Two. It's the same thing as the problem we did earlier with the number of A's even, just flipped.
And just to call them something else, let's call this Q2 and Q3. Let's make Q2 the start. If you go see B's, you go between them. If you see A's, you ignore them. Yeah. Okay. So we have these two DFAs. Which one's the accepting state?
Q2.
Yeah. Okay. We have these two DFAs. Let's take their Cartesian product and make one bigger DFA. So according to the construction, what we're going to first do is make a state for every possible pair of states. So what we're going to do is do a state here we'll call it 0, 2. We'll make a state here and we'll call it 0, 3. We'll put a state here, we'll call it 1, 2, and we'll put a state here, we'll call it 1, 3. Right? This corresponds to the Cartesian product of Q0 and Q2 and so on. What's the start state? 0, 2. Why is that the start state? Because Q0 is the start state and Q2 is the start state. What are the accepting states, if any?
1, 2.
Yeah. Now the hard part, transitions. Let's say we're at 0, 2. If we see an A, where should we go? Well, first we ask ourselves in our two DFAs here, where did they go? In the first one, if you saw an A, you stayed at Q0. And in the second one, if you saw an A, you stayed at Q2. So if you're in 0, 2, and the first DFA stays at 0, and the second DFA stays at 2, then you're going to stay at 0, 2. That transition takes one step, but it simulates doing two DFAs at the same time on a single step. Now let's say you're at 0, 2 and you see a B, what should you do? Well, you're here. If you're at Q0, you see a B, you go to Q1. So the first coordinate's gonna go to 1. Now if you're in the second DFA and you see a B, you'll go from 2 to 3. So if you see a B, where should you go? Okay, let's just do the rest of them. Let's say you're in 0, 3 at the same time and you see an A, where should you go?
Zero, 3?
Yes. Why? That transition and that transition. All right, if you're in 0, 3 and you see a B, where should you go? It's a bit tedious, but it's good practice.
1, 3?
Yes. No. If you see a B, you should go to 1.
1, 2.
Yes. Okay. You're in 1, 3. You see a. Where do you go?
0, 3?
Okay. And if you're in 0, 1, 3 and you see a B, where do you go?
1, 2.
Now, if you're in 1, 2 and you see an A, where do you go?
0, 2.
Yes. And if you're in 1, 2 and you see a B, where do you go?
1, 3.
There you go. So here's our Cartesian product DFAs. We took two DFAs, combined them to make one bigger DFA with a multiplicative growth, but this is the answer. Now, let's examine this. This DFA accepts what strings? It accepts the strings that reach both of these DFAs to accept. By the way, you can think of a DFA like a graph, and you can think of an accepted string like a path in the graph. A string is accepted by a DFA if it tells you how to get to the accept state, right? So what strings reach this accept state are exactly the strings that reach this accept state in the first DFA and this accept state in the second DFA, right? But what does that mean? It's the intersection of these two languages. So this DFA accepts strings, only strings, that both end with a B and also have an even number of B's. So it's the intersection. And in fact, we can assign a semantic meaning to each of these states, because each of them means something, right? If you're in state 0, 2, it means that you have seen what? It means that you were in state 0 in the original DFA, in the first DFA, and state 2 in the second DFA, which means that you don't end with a B and that you have an even number of B's. Right? So if a string ends in that state, that's the meaning, quote unquote, of that state. Similarly, if you're in state 0, 3, you don't end with B, but you have an odd number of B's. Right? So if you go between this state and this state, you don't end with a B, but you have an odd number of B's, right? 1, 2 is if you end with a B, and you have an even number of B's. And state 1, 3 means if you don't end with a B, you end with a B, but you have an odd number of B's. That structure becomes kind of apparent, right? When you go here, if you're in the bottom half, the last thing you saw was a B. And this then keeps track, okay, if you're in the bottom half, it means I saw an odd number of, I ended with a B, but I'm counting the number of B's to make sure I end with an even number of B's. That's what this keeps track of. And as soon as you see an A, you go above. When you're in the top half, then it's like, I didn't end with a B. And then as soon as you see a B, you go back to the bottom, right? So geometrically, you can kind of see both DFAs inside this DFA. Because this part is similarly just the counter here for this part, right? Those are kind of the same. So the DFA, you can assign meaning to it in this way. And this is the Cartesian product construction, right? Suppose I wanted to ask you for the union. This is a DFA for the union of two DFAs. Excuse me, the intersection. How would you make a DFA for the union? Yeah.
It's gonna be the same, but you have terminating state that are the you know.
You're almost there.
That are what's the word? What's the different that are the union of the two, right? So like for this, it's gonna be
So for the intersection, the final states are just the Cartesian product. For the union, you just change the final states. Because the union, you don't want to just land here, but you want to land here and here. Okay. But writing that out mathematically is actually quite difficult, so no one could ever fault you for this. I'll tell you it's annoying, but we know what it means. It's like Q1 times F2 union F1 times Q2. Something like this, okay? It's or, like one of them is accepting, not both of them are accepting. 1, 2 is accepting because 1 was accepting and 2 is accepting. But if we made these accepting, now this computes the union. Either of them accept. Okay? Questions on the Cartesian product construction of the DFAs? I have exactly one last sentence, and then we can go. It's just a definition. So we now have DFAs. We want to concern ourselves with what the power of DFAs are. Right? So we know, we use this curly L, and we say L DFA, B, the class of languages decidable by DFAs. So this is not a language. A language is a set of strings. This is a class, which is a set of languages. So it's a set of strings, right? And we know that if, for example, L is an LDFA, then there exists a DFA, let's say D, to decide L. That's the definition of this notation, right? What we have really proven is that if L1 and L2 are elements of LDFA, that this class of languages is closed under intersection. Then L1 intersect L2 is an element of LDFA. We've also proven that this construction you can just make a small modification to it because it simulates both DFAs. You only need to change the accepting criterion. So you just change it to be not just if both accept, but if any of them accept, and none of them. So that was enough for us to prove that that these languages are closed under union as well. The name for such a class of languages, by the way, is called regular. A class of languages is said to be, a language is said to be regular if there exists a DFA for it. If there's a DFA for it, it decides a regular language. If a language has a DFA to decide it, then it's regular. That's the definition of the regular languages. And we have now proven that the union of two regular languages is regular, and the intersection of two regular languages is regular. Pop quiz. Is the complement of a regular language regular? Again, this is the cool part about using set theory. We get that instead of like functions or something weird, we can ask such simple questions.
I'd say no, because we know there's some language that can't be done with a DFA, right?
But by asking if the regular languages are closed, I'll phrase the question for you.
Oh, I see what you're saying.
Let L be an LDFA.
Okay.
So
okay.
with that premise is L complement in LDFA. Now forget the non-regular languages, forget those other stuff.
Oh.
If you know that the language is regular, is this complement regular or not?
Yes.
Its complement is regular, why?
You can express it, the final set, the set of states that you accept as Q1, Cartesian product, Q2.
Forget the Cartesian product. Let's just suppose that there's a DFA.
You can express it as everything minus the union of two.
Almost. Let's say L has DFA. Let's call it Q, sigma, Q0, delta, and F. Okay? That's some diagram. What is the diagram, the DFA for L complement? You're like almost on the money. It is set operations, basically.
Everything is the same except the finite side is everything in Q that's not F.
Yeah. Flip all the states. Every accepting is rejecting, every rejecting is accepting. This is analogous to control F, return true, return false. Just swap those. Certainly you have a program now that does the exact opposite. Easy. So in fact, the regular languages are also closed under complement. If a language has a DFA for it, there's also a DFA for the complement. You just change the accepting and rejecting criteria. So there's two parts to the DFA. First off, the actual computation, the moving between states, the transitioning. Then there's the second thing, which is the accepting. The accepting is kind of arbitrary. You can just kind of like change it. You change the accepting, you change the answer, right? So if you just flip the accept and reject states, you get a completely different language. Easy. Final questions? All right. See you guys Wednesday.